Swayam Prabha. Digital India. Educated India.
In this lecture, we will continue our discussions on kinematics of rotation. We will start by looking at parametrization of rotation matrix. We have looked as an example in a previous lecture, we have looked at parametrization of rotation using yaw pitch rule. We are going to look at a few more of these parametrizations, and we are going to look at problems. Rotation can be parametrized by Euler angles. What is the meaning of parametrization? You know that a rotation can be fixed normally. I mean, this is a common knowledge that rotation can be fixed by specifying three quantities. Now, how do you form these three quantities? How do you find these three quantities, or what representations, which three quantities, what are these three quantities? That is answered by parametrization. Therefore, we will have a rotation matrix which is a function of, this matrix is a function of certain parameters, and in terms of which I can represent this rotation. For example, in yaw pitch rule, the angle psi, theta and phi, they parameterize the rotation. Similarly, in Euler angles, we can use Euler angles. 313 means first rotation is about z, second rotation is about the new x, and the third rotation is about the new z. So, every time successive rotations are about new axis, and 313 means z axis, new x axis, new z axis, 313. So, what should be 321? First rotation is about 3, which is z, second rotation is about new y, third rotation is about new x. That means, first rotation is about z0, second rotation is about y1, third rotation is about x2. We have already looked at yaw pitch rule, that also is a parametrization. We will look at Euler axis angle parametrization and Euler parameters, which are also known as unit quaternions. Euler angles 313. So, just now I mentioned is 3, first rotation is about z0 by an angle phi, rotate by phi about z0, get the rotation matrix, rotate by an angle theta about the new x axis, axis 1. So, this is x1 and get the rotation matrix R from 2 to 1. The third rotation is about the new z, which is z2 by an angle psi, and get the third rotation matrix 3 to 2, rotation matrix R from 3 to 2. This is R from 1 to 0, the first rotation by about z. By now, you should be conversant how to construct these matrices. R 2 to 1 is a rotation about x axis by an angle theta. R from 3 to 2 is a rotation about the new z2 axis by an angle psi. Net transformation is the product of these three matrices in this order, because every time this is post multiplication in this order, because every time we are doing the successive rotations about the new axis frames. This you can calculate and find out, I will leave it to you. Yaw pitch rule, we have already discussed this, rotate by psi about z0, that will give you the rotation matrix R from 1 to 0, rotate by theta about y1, the new y axis, that will give us rotation matrix R2 to 1, and rotate by phi about x2, the new rotation, new x axis, that will give us r from 3 to 2, and these are the rotations are yaw, pitch and roll. Here they are shown finally. These are the matrices, and we have actually looked at the product. We have already seen this product, you can check this. Now, we come to the Euler axis angle parametrization. For that, first we look at the Euler rotation theorem. The Euler rotation theorem says any motion of a rigid body with a point of the body or its extension fixed can be expressed as a single rotation about a fixed axis. Any rotation, any motion of a rigid body with a point of the body or its extension fixed, any motion of a rigid body with one point fixed, one point of this rigid body or its extension fixed can be expressed as a single rotation about a fixed axis. Suppose you rotate by an angle theta about this unit vector n cap. I have shown some n cap direction, and I have shown the angle theta, and this purple frame was initially coincident with the black frame, and after this rotation, this is the configuration shown after the rotation has taken place. And this unit vector is a direction. So, I mean because it is a direction, it has to be a unit vector, and n x square plus n y square plus n z square is 1, and this we have already discussed. The rotation matrix representing a rotation of angle theta by about a unit vector n cap is represented by this. We have derived this, and it is not very difficult to remember also. You can remember this expression of a general rotation matrix, where n cap is the Rodrigues form of n cap vector, and Rodrigues form, recall, is a skew symmetric form, and this is a very special structure. Please remember this. We can calculate n cap Rodrigues form and its square. N cap Rodrigues form is there, and now I have also calculated the square of it. Sometimes this is written in a slightly different manner, because you the first one term, this term is minus n y square minus n z square, and you know that n x square plus n y square plus n z square is 1. Therefore, sometimes you can also write this as n x square minus 1. This is n y square minus 1, this is n z square minus 1. So, I have written it. Now, let us look at the visualization of Euler axis angle. Consider a solid sphere of radius pi in 3-dimensional Cartesian space. Now, what I am trying to get at is visualizing rotation. Normally, we visualize path of a particle or motion of a rigid body, we visualize as the motion, let us say, of the center of mass and its rotation, but we do not have a very clear visualization of rotation. How do I understand these three angles? How do I understand visualize a path? This Euler axis angle theorem, this allows us, or it helps us to visualize this. Consider this solid sphere of radius pi in 3-dimensional Cartesian space. Now, any orientation of a body by Euler's axis angle theorem can be represented by a unit vector and a rotation about that unit vector. If I now form a vector q, which is this angle in radian times the unit normal about which the rotation has taken place, and this I say represents this orientation. this vector I say represents a orientation. It represents the orientation of a body, let us say. It represents an orientation. This vector now represents an orientation, and this is a 3 cross 1 vector, right. So, it has a representation in some Cartesian space. Any point inside this sphere of radius pi will therefore represent an orientation, like this red dot represented by this vector q, whose magnitude is the angle of rotation and whose direction is the direction about which this rotation is taking place. That uniquely represents this rotation, this orientation, because given this theta and n, or given this vector q, I will take the magnitude, I will take the unit vector direction. Whenever I am given a q vector, I will take its magnitude and interpret that as the rotation in radians, and I will take the unit vector of q and say that that is the direction about which that rotation has to be given, and that will specify my orientation of the body. Therefore, orientation will be represented by this vector q, whose magnitude is the rotation angle in radian, and the direction is that n cap, the direction of rotation, the axis of rotation. Why am I saying radius pi? The orientation, when you reach when you have such an orientation vector q with radius with rotation of pi radians and minus pi radians about the same unit vector. That means, suppose I take a point here, the length of this is pi and the direction is some n cap, magnitude is pi, and I consider just the opposite thing, just diametrically opposite point, because now we are on the surface of that sphere. Sphere has radius pi. On this side I take pi, on this side I take minus pi, n cap multiplied by minus pi. Then I reach this point. Now, just think for a moment, the rotation of a body about any axis by an angle pi radians and minus pi radians will lead you to the same orientation. Therefore, this point and this point on diametrically opposite, the diametrically opposite points of this sphere are identified, they represent the same orientation. A rotation by pi and a rotation by minus pi about a single axis gives you the same orientation of a body. Therefore, these are called antipodal points. The antipodal points are identified. Pi n cap represents the rotation, minus pi n cap also represents the rotation, and these two represent orientations of a body. Pi n cap represents one orientation of the body, minus pi n cap represents the same orientation of the body. It represents the same orientation of the body. So, if you rotate a body by pi, or if you rotate by a body by minus pi, you will reach the same orientation. Therefore, antipodal points of this radius pi sphere in 3-dimensional space they are identified, they are called antipodal points, diametrically opposite points. Now, if you consider any point, any 2 points, say this is one point and this is another point, this red one is another point, this is another vector representing orientation. Now, any path joining these two orientations is a path, change of orientation path. It could be a straight line. You can think of other paths. Interestingly, you can also think of paths like this that go out from they reach the surface of the sphere, come back, because that point is same as its antipodal point, it is identified with the antipodal point, and from here you come back and join the new orientation. Let me redraw this again. Suppose you have another orientation here, you can traverse this path, you go up to the surface of the sphere, go to the diametrically opposite point, these two diametrically opposite points are identified. So, you have traversed up to here, and that is same as this orientation, and now from here you traverse this. This is a path. This is also a path. You can directly travel as well. You can directly travel. There are various kinds of paths. Any point inside or on the boundary represents a rotation or orientation of a body, and you can join them by paths, and that implies change of orientation. Change of orientation is represented by a path within the sphere, or you can reach the boundary of the sphere and switch to the antipodal point and again continue inside. The path reaching the boundary can enter the sphere from the antipodal point. So, this gives you some visualization of orientation and its change, the path along which it changes. Now, you can define, for example, what is the shortest path or what is the best path to go from one orientation to another. You can make these you can formalize these things based on this picture. Let us look at a problem. A panel is moved from position indicated by A, B. These two are representing the two corners. So, there is a plate on which advanced dynamics may be written. The panel is moved from position indicated by A comma B, which names the two corners, because we have to track them, to a new position shown by A prime B prime, which means this A travels to A prime and B travels to B prime somehow. I can always take that A to A prime and I can take B to B prime. So, somehow they travel. Determine the rotation matrix R, this is the first. Also determine a single axis and rotation that will take the panel from the initial orientation to the final orientation. This motion, in this motion of this plate, one point is fixed, that corner point which lies at the origin of the x 0, y 0, z 0. Therefore, we can find out a single rotation, about a single axis, a rotation about a single axis. Now, rotation matrix, let us first try to go, somehow we try to go and figure out what is the rotation matrix. The first step can be, for example, I rotate and you can actually find other paths as well. I am finding one path, you can find out various other paths. I will first rotate this plate by an angle 180 degree about the z naught axis. What will happen if I rotate about z naught axis? This, let me first draw this. If I rotate by an angle 180 degree about the z naught axis, this is going to rotate and come here. Therefore, this AD, advanced dynamics, will now face the other side, not towards us. And then in the second step, I am going to rotate about this y1 or y2 by an angle 90 degree in the negative y direction, then it will come to the second position. You can think of other ways. For example, the first rotation can also be a pi rotation about x naught. You can figure out. Let us then represent these two rotation matrices. First one is about z naught by an angle pi, the second is about y 1, because y naught then will go to y 1, about y 1 by an angle minus pi by 2. See the rotation of 90 degree, it is in the negative y direction, and these two are successive rotations which are defined in the new frame, every time in the new frame. You can think of rotations that will take from the configuration 1 to configuration 2 by always rotating about the old frame, and you should try this. Okay. We have done these two steps and we have taken rotation about the new frame every time, therefore, it is post multiplied, that same sequence rotation matrices are post multiplied, that will give me r from 2 to 0. And if you do it, if you do this calculation, I will leave it to you. Now it should be very standard calculation, you will get this rotation matrix. The next part of the problem asks us to find out a single axis and a rotation about which this orientation changes can be possible. So, we have to find out a single axis and rotation. Therefore, we have to find out the Euler axis angle form, which is this. We have derived this and it is quite easy to remember, and we have to find, therefore, now we have to find out n cap and theta. The problem is reversed. Initially we were thinking we are given n cap and we are given theta, what is the rotation matrix? Now the problem is reversed. We are given the rotation matrix, we are asked to find out n cap and theta. Here I have written out the whole of the rotation matrix in terms of n cap and theta. I have used a notation which is typically used, this is called versine, which is 1 minus cosine theta, or verse, in short, verse of theta is 1 minus cosine theta. You will note that the trace of this in this form, the rotation matrix written in this form, and if you take the trace of this rotation matrix, you will get versine theta, verse theta plus 3 cosine theta. Why? Because nx square plus ny square plus nz square, this will come and v theta will turn out common, and nx square plus ny square plus nz square is 1. Therefore, we will get verse theta plus 3 cosine theta is equals to minus 1, that is from this trace of this matrix, that is minus 1. Therefore, cos theta is minus 1, theta is 180 degree, and it can be minus 180 degree as well. The other calculation, you see that nx square, now I know theta, therefore, I can find out any of these elements. For example, nx square, say this element nx square, this is verse theta, first element is 0. From here I can solve for nx, and but there is a choice of sign, because this comes as square. So, this has this nx turns out to be plus minus 1 by root 2. Second, I look at this element, because you see V, what is verse theta, because cos theta is -1 and verse theta is V theta is 1 minus cos theta. So, V theta from here must be 2, that is what I have used. So, this n x square plus into 2 plus cos theta is -1 equal to 0, and from here n x. Similarly, from this element I find out n y is 0, and from this element I get z as plus minus 1 by root 2. Therefore, I can choose one of the signs consistently, like if I take plus for n x, I must take plus for n z. If I take minus for n x, I must choose minus for n z. They will give me the same orientation. Therefore, n cap, the unit vector is 1 by root 2, 0, 1 by root 2. And what is this unit vector? This is our answer, and theta is pi, of course, which we have found out. And what is our vector? 1 by root 2, 0, 1 by root 2. Therefore, it has projections in x and z. This is the vector. I have drawn that vector. It makes an angle 45 degree. It is on the x z plane, makes an angle 45 degree. If you rotate by 180 degree about this axis as shown here, you will bring this orientation to this orientation. So, here in this problem we have solved for the single axis rotation that is required to bring the first configuration to the second configuration, and this procedure will remain the same for any such calculation. So, to summarize, we have looked at parametrization of the rotation matrix and looked at some problems. We have solved the inverse problem this time. Given the rotation matrix, find out the angle theta and the unit vector about which this rotation has to be made to reach or to attain a new configuration, a new orientation. So, with that I will close this lecture.